Welcome to the CWI Deep Dive Podcast series. This is one episode in a series of 11, each covering a chapter of Welding Inspection Technology. These podcasts are designed for inspectors preparing to take the American Welding Society Certified Welding Inspector exam. They are not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but to complement them. Along with our CWI Test Prep app, available on the Apple App Store, these podcasts will help strengthen your preparation. You can continue learning at work, during your commute, or wherever you find time. Today's episode is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. Learn more at the link in the video description. And just a quick heads up before we dive in. This podcast is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this podcast is not a replacement for purchasing or studying the original text. Our goal is to provide commentary, explanations, and reinforcement to help inspectors prepare for the Certified Welding Inspector exam. Okay, let's get started. Today we're tackling Chapter 5, Weld Joint Geometry and Symbols. This is really the language of welding, isn't it? The way everyone from the engineer to the welder to the inspector stays on the same page.
Absolutely. Misunderstand this and, well, you're setting yourself up for problems right from the start. It's the blueprint language.
So let's talk basics. If you, as an inspector, walk up to a fit-up and see something wrong, you need the right words. What are those fundamental joint types we need to know?
Yeah, you got to have these down cold. There are 5 basic ones that cover, almost everything you'll see. You've got the butt joint, the corner joint, T-joint, lap joint, and then the parallel or edge joint.
Butt, corner, T, lap, edge. Got it.
Those 5, nail those down.
And just knowing the joint isn't quite enough, right? We also need to understand the pieces involved, the members, and how they might move.
Just a quick interruption to introduce a resource to help you take your training further. The AMS Level 3 CWI Part A Test Prep app is now available on the Apple App Store. Designed for welders and inspectors preparing for the Certified Welding Inspector exam, it offers 2 modes. Study mode gives instant feedback with detailed explanations, and test mode simulates real exam questions with topic-based results to track your progress. All questions align with the AWS Welding Inspection Technology reference, ensuring accuracy and relevance. Download the CWI Part A Test Prep app today on the Apple App Store, and take your study time to the next level.
Exactly. It gets a bit more technical there, but it's about expected stress and movement. So, a butting member. Think of a butt joint. It's restricted. It can't really move perpendicular to its thickness easily.
Okay, like 2 plates being joined end to end.
Spot on. Then you have a non-butting member. This one is free to move perpendicular to its thickness. Think about a lap joint. Those plates can slide a bit relative to each other before welding.
Makes sense.
And sometimes you might see a splice member. That's like a patch or a plate that spans across the main joint, maybe connecting pieces that aren't perfectly aligned or the same thickness.
Right, bridging the gap.
Kind of.
Yeah.
And sometimes, though it's less common, you might even need a joint filler plate inserted in there too.
All right, so we have the joint types and the members. Now let's zoom in on the geometry before welding. What are inspectors looking for and measuring during fit-up?
Okay, this is pre-weld prep verification. Super important. You're looking at the shape of the gap, essentially.
Yeah.
We start with the joint root. That's simply the point or line or even area where the members come closest together before welding.
The closest point.
Yeah.
And the surfaces that form that gap.
Those prepared surfaces within the groove. That's the groove face.
Okay.
And right at the bottom of that groove face, at the joint root, you have the root face. People often call it the land. It's that little flat surface.
The land. I've heard that.
Yeah. Now, if that land's width shrinks down to basically nothing, it becomes a root edge. It's a subtle difference, but calling it the wrong thing on your report, well, that can cause real issues later.
So land means thickness, edge means 0 thickness. What about the gap between the members?
That's your root opening. Simple enough. And then the angles come into play. The angle of the cut on a single piece is the bevel angle or chamfer angle. Put the 2 pieces together and the total included angle of the groove is the groove angle.
Got it. Bevel is one piece. Groove is the total angle between the 2.
Exactly. You need all that terminology just to describe the joint before a single spark flies.
Okay, geometry set. Now, we actually picked the weld type. AWS A2.4 gives us 8 basic types. Let's focus first on groove welds. There are quite a few variations. What drives choosing, say, a U-groove over a V-groove?
Good question. It usually boils down to two things:
Mm.
cost and accessibility. You've got 9 common groove types listed: square, V, bevel, UJ, flare V, flare bevel, scarf,
Yeah.
and then the backing welds, which we'll get to. Now think about thick material. A V groove is simple to prepare, maybe just grinding or flame cutting, easy prep, but it creates a large volume that needs filling with weld metal.
Lots of weld metal, lots of time.
Exactly. Now, J and U grooves are designed with curves at the bottom. This shape drastically reduces the amount of weld metal needed to fill the joint compared to a V groove of the same depth.
Ah, so less filler metal, less welding time. Sounds good.
It is,
Yeah.
but preparing those precise J and U shapes, that often requires machining. Much more expensive prep work, so it's a trade-off. Save on welding, spend more on prep. You need to understand why a procedure might call for one over the other.
That makes sense. And you mentioned back and backing welds. That's a classic exam point, right? The difference.
Oh, yeah, they love this one. It's all about timing and what it does. A back weld is put in after the main weld on the front side is done. Often you'll back gouge the root of the first weld, then apply the back weld to ensure fusion or create a specific profile. It's a finishing step, kind of.
After the main weld. Okay.
A backing weld, however, is put in before you even start the main weld passes. Its job is to support the molten pool of the first root pass from underneath, prevents melt-through, ensures good penetration.
So backing is first for support, back is later for refinement or completion.
You got it. Mix those up, and you've misunderstood the whole planned sequence.
Okay, let's pivot. Probably the most common weld type out there. Fillet welds. Pronounced fillet, right?
Correct. Fillet.
Yeah.
Yeah, you see these everywhere. They have that roughly triangular shape, joining surfaces usually at 90 degrees. Think lap joints, T-joints, corner joints.
And a big advantage is less prep.
Generally, yes.
Yeah.
They often don't need edge preparation like groove welds do, which simplifies fit-up quite a bit, makes them very popular.
Sometimes you don't need a fillet weld running the entire length of the joint, though. We use intermittent welds then.
Right. If the design doesn't require a continuous weld for strength or sealing, you can use intermittent welds to save time and material. The two main patterns. Imagine looking down on a T-joint from above. If you have weld segments on one side, directly opposite the segments on the other side, that's a chain intermittent fillet weld.
Lined up.
Exactly. Now, if you offset them, so a weld segment on one side is placed in the middle of the gap between segments on the other side. That's staggered intermittent fillet weld.
Okay, chain and staggered. Got it.
Those patterns help manage distortion too sometimes.
Good point. We should also briefly touch on plug and slot welds. What are they?
These are for joining overlapping members, where you weld through a hole in the top piece to the piece underneath. If the hole is circular, it's a plug weld. If the hole's elongated, like a racetrack shape, it's a slot weld.
Okay, welding through a hole.
But here's the key distinction for inspection and symbols. If you put a fillet weld inside that hole or slot, it's not technically a plug or slot weld anymore. It follows fillet weld rules and symbols. That's a common point of confusion.
Okay, so the type of weld in the hole matters.
Precisely. And finally, just to round out the types, there are surfacing welds. These aren't usually for joining parts together, but for modifying the surface. You see build up to restore worn dimensions, buttering to put down a layer of compatible metal before joining dissimilar materials, cladding for corrosion or heat resistance, like on the inside of a vessel, and hard facing for wear resistance on things like excavator teeth.
Modifying the surface, not joining, makes sense.
They all have specific applications, often in repair or specialized manufacturing.
Okay, we've covered prepping the joint and the types of welds. Now the weld is complete. As inspectors, we need the language to describe what we see, especially if there are issues. What's the terminology for a finished weld?
Right, post-weld assessment. Crucial vocabulary here. For any weld, you have the exposed surface, which is the weld face, and where that face meets the original base metal, that line is the weld toe.
Face and toe. Okay.
On the other side, especially if it's only welded from one side, you have the weld root, the point of deepest penetration, and the exposed surface of that root penetration is the root surface.
Gotcha. What about the extra metal piled up? Reinforcement.
Yes, weld reinforcement. It's the weld metal proud of the base metal surface. Face reinforcement is the reinforcement on the side you welded from, sometimes called the crown or cap. Root reinforcement is the reinforcement protruding on the back side, the root side. But, and this is important, it only applies to joints welded from one side. If you weld a joint from both sides, both bumps of excess metal are technically face reinforcement.
Ah, good distinction. Okay, now for fillet welds again. Measuring them seems straightforward, but then we hear about different throats. Why are there three? Theoretical, effective, actual. Which one matters most to us?
Yes, the throats. It seems complicated, but it's because we need to account for the ideal geometry versus the real-world result, including penetration and shape. First, the theoretical throat. This is purely geometry. It's the shortest distance from the joint root to the hypotenuse of the theoretical triangle, assuming perfect fit-up, zero root opening, and minimal penetration. It's a calculation starting point.
Okay, theoretical. What's next?
Effective throat. This is usually what designers use for strength calculations. It's the minimum distance from the root of the weld to its face, minus any convexity. It represents the minimum plane through which the weld might fail.
So it accounts for the weld shape a bit, ignoring the bulge.
Kind of, yes. It assumes adequate fusion, but focuses on the minimum load-carrying dimension.
And the third one, actual throat.
The actual throat is what you, the inspector, are often trying to assess or verify. It's the actual shortest distance from the weld root to the weld face. Crucially, it includes the effects of penetration beyond the root and any convexity.
So this is the real-world measurement.
Exactly. Your job is often to ensure that the actual throat achieved meets or exceeds the specified effective throat required by the drawing or symbol, which means you need to verify sufficient joint penetration.
Speaking of penetration, let's clarify those terms.
Sure. Depth of fusion is how far the weld metal melted into the base metal or previous pass, measured perpendicular from that fusion line. Joint penetration is more about the overall depth the weld extends into the joint itself. For groove welds, it's essentially the weld size.
And if it doesn't go deep enough?
That's incomplete joint penetration, or IJP, a serious discontinuity where the weld metal fails to reach the required depth or extend completely through the joint thickness. Big red flag.
Definitely. One more term before we hit symbols. The area around the weld.
Yes, the HAZ. The heat affected zone. This isn't melted metal, it's the base metal right next to the weld that got hot enough during welding to change its microstructure and therefore its properties.
So not weld metal, not original base metal, but something in between.
Pretty much. Its properties can be very different, sometimes harder, sometimes softer, depending on the metal and the process. It's a critical area for potential cracking or other issues, so we inspect it carefully.
Very important. Okay, let's take a quick pause here. We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
All right, we've covered joints, welds, and terminology. Now the big one, how all this information gets communicated on a drawing using the welding symbol. First, help us with the basic terms. Is there a difference between a weld symbol and a welding symbol?
Yes, absolutely, and it's a fundamental distinction. The weld symbol is just the little graphic that shows the type of weld. You know, the triangle for a fillet weld, the V shape for a V groove, the little rectangle for a plug weld.
Just the picture for the weld type.
Exactly. The welding symbol, however, is the entire thing. It includes the horizontal reference line, the arrow pointing to the joint, the weld symbol itself, plus all the dimensions, notes, and any other supplementary symbols attached to it. It's the whole package.
So the welding symbol contains the weld symbol plus more. Correct. And every welding symbol must have at least two parts. The reference line and the arrow. Those are mandatory.
What about that little fork sometimes at the end, the tail?
The tail. It's optional. It's only used if you need to add extra information that doesn't have its own symbol, like specifying the welding process, GMAW, SMHW, referencing a specific procedure, WPS number, or some other note. If there's no extra info needed, you just leave the tail off.
Okay. Reference line. Arrow are required. Tail is optional. Now, the absolute core rule, side significance. How does that work?
This is non-negotiable. You have to get this right every single time. The reference line divides the world into two locations, arrow side and other side. Information placed below the reference line refers to the arrow side of the joint, the side the arrow is physically pointing to.
Below means arrow side.
Information placed above the reference line refers to the other side of the joint.
Above means other side.
Simple as that. If the fillet symbol, triangle, is below the line, you put the fillet weld on the side the arrow points to. If it's above the line, you put it on the opposite side. If symbols are on both sides, well, you weld both sides.
Seems clear enough. But what about welds like a bevel groove, where only one piece gets the angled preparation? How does the symbol tell you which piece to bevel?
Excellent point. That's where the broken arrow comes in. If the weld type requires preparation on only one of the two members being joined, think bevel grooves, J grooves, the arrow line itself will have a sharp break, a corner in it. That break always points directly towards the specific member that needs to receive that preparation.
So the break points to the piece to be prepped.
Must point to it. If the arrow is straight, it implies either no prep is needed, like a square groove, or both sides get symmetrical prep, like a V groove. Missing a broken arrow or misinterpreting it leads straight to fit-up errors.
Crucial detail. Okay, let's talk dimensions on the symbol. Starting with our friend the fillet weld, where does the size go?
For a fillet weld, the size, which typically refers to the leg length, always goes to the left of the fillet symbol, the triangle.
Left of the symbol.
And critically, the size is not put in parentheses, just the number. If you see a number in parentheses next to a fillet symbol, it means something else entirely, usually length for contour finishing.
Okay, size left, no parentheses. What about the length?
Length goes to the right of the symbol. If no length dimension is given, it means the weld should be continuous for the full length of the joint shown on the drawing.
Makes sense. And those intermittent welds we talked about, chain and staggered.
Right. For those, you still have the size to the left. To the right, you'll see two numbers separated by a hyphen. The first number is the length of each weld segment. The second number, after the hyphen, is the pitch. That's the center-to-center spacing between the segments.
So like 14 size on the left, then symbol, then 2/6 length pitch on the right.
Exactly. 14-inch fillet, 2 inches long, spaced, 6 inches center-to-center.
Okay. Now, dimensioning groove welds seems a bit more complex, with D and S sometimes showing up.
It is a bit more involved. For most groove welds, like V, bevel, U, J, you might see two dimensions next to the symbol, both to the left. The first number, right next to the symbol, is the depth of bevel, or depth of preparation, often shown as D conceptually, though the letter D isn't usually written on the symbol itself.
Depth of prep.
Then, usually immediately following that, in parentheses, is the groove weld size, conceptually S. This S in parentheses indicates the required joint penetration. So you'll see something like 12/58. That means prepare the groove 12-inch deep, but ensure you get 58-inch of penetration.
Prep depth, then required penetration in parentheses, both on the left.
Correct. The main exception is a square groove weld. Since there's no bevel prep, you only show the required penetration S. And it's not in parentheses for square grooves. It's just shown to the left of the square groove symbol.
Okay, that's a specific exception. What about root opening?
If a specific root opening is required, that dimension is placed inside the V, bevel, U, or J weld symbol itself. Like you'll see 18 written inside the V symbol.
Inside the symbol for root opening. Got it. This brings us to CJP, complete joint penetration. How is that shown or not shown?
Right. This is another common exam topic because it relies on the absence of information. If you have a symbol for a single groove weld, like VU, bevel J, or a symmetrical double groove weld, like double V, and both the depth of preparation D and the weld size S dimensions are omitted.
No numbers on the left.
No numbers for D or S. Then the symbol requires CJP, complete joint penetration. The weld must extend completely through the thickness of the joint. The lack of dimensions is the instruction for CJP in those cases.
Wow, okay, so no dimension means full dimension, basically.
For CJP on those specific weld types, yes. You have to know that rule.
All right, beyond the basic types and dimensions, there are supplementary symbols adding more detail. What about controlling the final shape of the weld face?
Yes, we use contour symbols. These are placed above or below the weld symbol, depending if it's arrow or other side. A straight flat line means the weld should be finished, flush with the base metal. A curved line arching upwards means a convex contour is required or acceptable. A curved line dipping downwards means a concave contour.
Flush, convex, concave. Simple graphics.
Pretty straightforward. And if a specific method is required to achieve that contour.
Like grinding.
Exactly. You put a letter above the contour symbol. G for grinding, C for chipping, M for machining, R for rolling, H for hammering. But big caveat, the letter only tells you the method. It does not specify how smooth the finish needs to be. That would require a separate note or specification.
Method, not quality of finish. Good point. What about symbols indicating where the weld happens or if backing is used?
Okay, location first. If the weld needs to be made out in the field, not in the fabrication shop, you add the field weld symbol. It looks like a little flag sticking up from the junction of the arrow and reference line. Flag means field weld.
Flag means not in the shop.
Got
it.
Then there's the melt-through symbol. This is a filled-in semicircle placed on the opposite side of the reference line from the groove weld symbol. It specifically requires CJP plus visible root reinforcement on that backside. You need to see that penetration clearly.
Melt-through needs visible root reinforcement. Okay. Now, the really confusing one, backing symbol versus backing weld symbol. Let's clarify that again.
Yes, let's nail this down. They sound similar, but are totally different. The backing symbol looks like a rectangle placed on the opposite side of the reference line. It indicates that some kind of material like a copper bar, ceramic tape, or even part of the structure is being used as a temporary or permanent backing to support the weld root. It is not a weld itself.
It's a physical thing used for support.
Exactly. And if that backing material needs to be removed after welding, they put an R inside the rectangle symbol.
R means remove the backing material.
Correct. Now that is completely different from the backing weld symbol, which is the same symbol as a groove weld, like the bead symbol, placed on the opposite side, indicating that a preliminary weld bead needs to be applied before the main weld, as we discussed earlier. One is material support, the other is an actual weld bead.
Okay, rectangle symbol, backing material. Weld symbol, backing weld bead. That's clearer.
Good. Also, don't forget the weld all-around symbol. It's a small circle drawn right at the elbow where the arrow line meets the reference line. It simply means weld completely around the joint indicated.
Circle means go all the way around.
Yep, though technically it's often considered redundant for a simple butt weld on a pipe, since you'd assume that's welded all around anyway, but you'll see it used frequently.
Okay. Lastly, sometimes drawings specify sequences to control distortion. Can you quickly review those?
Sure. Welding introduces heat. Heat causes expansion and contraction, which leads to distortion or warping. So sometimes sequences are specified. The backstep sequence. You're welding overall, from left to right, let's say, but each individual small weld bead or segment is deposited from right to left. Stepping back against the overall direction of progression helps balance the heat input.
Okay, welding backwards in small steps.
Kind of. Then there's the block sequence. You divide the weld into separate blocks or sections. You might weld section 1 completely, then jump to section 3 and weld it, then go back and weld section 2 in between. Or you might weld layers within blocks in a specific order. Spreads the heat out over the structure.
Welding in separated blocks.
And finally, the cascade sequence. This is often used in thicker multi-pass welds. You lay down passes in overlapping layers where each subsequent pass is a bit longer than the one beneath it, creating sort of a cascade effect up the joint face. Again, manages heat and shrinkage stresses.
Backstep, block, cascade, different ways to manage the heat.
Precisely. Control distortion.
Excellent. That covers a huge amount of ground from Chapter 5. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and Federal Aviation Administration readiness. To learn more, visit amslsl3.com, and don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.
So as we finish up here, the big takeaway is that the welding symbol isn't just a drawing element. It's really a set of legally binding instructions. Getting those subtle rules right, like the broken arrow or the difference between theoretical and actual throat, or CJP requirements, or backing symbol versus backing weld that's fundamental for an inspector. Getting it wrong means non-compliance, delays, and potentially very expensive rework.
Absolutely. It is the core communication tool. So here's your challenge as a CWI candidate listening to this. Go find some complex welding symbols in your study materials. Look for ones that combine groove welds, fillet welds, maybe some contour or field weld symbols. Then really force yourself to mentally translate that entire symbol back into a 3D picture of the joint preparation and the finished weld. Sketch it out if you need to. If you can look at a complex symbol and instantly visualize exactly what needs to happen physically, then you're well on your way to mastering Chapter 5.
That's the real test.
That's it for this deep dive into weld joint geometry and symbols. Keep practicing those symbols, reinforce the knowledge, and we'll catch you on the next one.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support. NDT Level 1, $1 per month, NDT Level 2, $2 per month, and NDT Level 3, $3 per month, or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.